Better now. Thank you. Maddie heard two of us.
This is a reflection sheet.
Okay. Good afternoon, everybody. Let's keep grinding. I got maybe another week left of hydrogen. We'll move on to more interesting atoms next week. So it's just I know it's probably a little overwhelming, Maddie. So let's do that about hydrogen today, and let's spend a day looking at the orbitals. Okay. I don't like to spend too much on orbitals because I don't think they're all that interesting. But just enough that we have an appreciation for the orbitals, that when we do need them, which is we're going to need them for bonds. Obviously, when we combine two atoms together, we better think about where the electrons are. It's going to be useful there. Well, what I want to look at is, in particular, I want to focus today, not so much on, we know what the 1s and the 2p's and all this look like in inorganic and GenChem. They're not so much different in the PChem world. So it's not, but what I would like to learn a little bit is about the math, and just kind of the general structure of these orbitals and what they look like in space. And so we'll draw some pictures and look at some equations, and I want to give you an intuitive sense of how the hydrogen atom works just by looking at the orbitals. And then what we'll do on Wednesdays, we'll look at energies, and we'll start to think about energies of the electrons in hydrogen, or of the electron in hydrogen. There's only one. I'm gonna go from there. So last class we derived indirectly these radial solutions to the problem. Remember, we saw the angular problem weeks ago. We had these spherical harmonics that describe the behavior of the electron at some fixed radius, moving around in this orbit, elliptical orbit. What we needed to finish out was now thinking about the energy and the kinetic energy, the potential energy of the electron as a function of distance from the proton instead of angle. And that was a much more complicated problem. It depended on the angular part, because the faster the electron spun, the more centrifugal force it had, the harder it pulled away from the proton. And so when we think about the radial equations, the radial behavior of the electron, we got to think of the balance of the electrostatic attraction and the repulsive force that arises from the angular momentum, the centrifugal potential. So we had this balance of two forces. That's what Bohr identified, a balance between electrostatics and centrifugal force. And we solved the Schrodinger equation with that assumption. We have this kind of complicated equation that we're going to walk through today. I'll look at some examples. And we'll see that things will simplify very nicely when we start to look at specific states. But let's just go back through the idea of this radial wave function. Remember the idea of the way we tackled this on Thursday for like the 6 people who were here, was that we looked at the solutions at really, really small r, which is where the centrifugal potential starts to kick in big time, where r squared is large compared to r. And we looked at really long r goes to infinity, where the electrostatic force is stronger than the centrifugal force. R1 over r decays more slowly than 1 over r's. And we saw that at r0 close limit, the wave function, the radial function, looks like a polynomial. It looks like r to the L, where L is the angular minimum. And at long distance, it looked like an exponentially decaying function, e to the minus r. And so what we had to figure out was the intermediate region, where r is kind of in its sweet spot. It's not too close, it's not too far. And we had an idea that probably the way that this should look like an intermediate is just like the harmonic oscillator. It should look like a wave. It should oscillate in the middle, right? Where the region in which the electron is mostly existing, it should look wave-like. Right? So we should have some sort of oscillatory orthogonal function, some behavior in the middle of the orbital, kind of an intermediate distance, not at small r or large r, but in the middle. And remember in the harmonic oscillator, when we looked at that middle region, which was the region inside the potential, it looked like a polynomial function as the function of the excitation. So we had this x squared, or x plus x squared plus x cubed, depending on what level we are, that Hermite polynomial, as we call it. And we have the same kind of polynomial at intermediate in the hydrogen atom, called the Laguerre. And it's just a function of r nothing particularly crazy. But it provides that oscillatory behavior at intermediate distance. It also provides the orthogonality of the functions that we need for the 1s, 2s, and all of the functions to be completely separate. So, what again this awful looking thing, but this is all effectively plug and chug. We pick a value of our two quantum numbers for radial, n, that's our new number, the radial quantum number. That specifies which orbit we're at in radius. That starts with 1, 2, 3, 4, 5. That's the 1 in the 1s, or the 2 in the 2s, the n. And then there's also depends on the angular momentum. Of course, the more angular momentum you have, the more centrifugal force you have. That changes your radial behavior. So it depends on L. And L varies, as we find out, in a radial system between 0 and n-1. So what that means is that when you are balancing angular momentum and electrostatics, L can't be any value it pleases. When a system is freely able to rotate, just the angular problem alone, there's no electrostatic glue, right? It's a free rotation. We saw that L could be any value it pleases. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. You can basically fix an electron, fix a particle with some other particle and let it spin as much as possible. And any L is acceptable. But here we have a slightly different situation. The electron here is not rotating freely, but it's balancing its rotational act with its electrostatic act, the radial attraction. And so you always have a balance of these two forces. So if you take L to be too high compared to N, L is the system spinning so fast that the electron's just going to fly away. Right, it's going to be so much angular momentum that the electron's orbit is not stable, and it just leaves the orbit. So we don't want L to be too large at a given N when the centrifugal force is greater than the electrostatic force. That's an escaping electron. So L has to be dependent on N. The different N's give you different L's, and so on. And that gives us the 1s, 2s, 2p structure, right? There is no 1p, there is no 2d, right? There's no 3f, right? The only things that are allowed for a given N are L's that are up to n-1. So if N is 1, L can only be 0. If N is 2, L can only be 0 and 1. That means you have 2s and 2p. And as 3, you can have L 0, 1, and 2. That's S, P, and D. And as 4, you can have up to F. L equals 4. L equals 3, excuse me. Right? So the allowed solutions of our balance between centrifugal force and electrostatic attraction gives us the orbital structure that we learned in Gen Chem. You have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and so on and so forth, right? So that comes from that stability between the two forces in the system. Let's go look at this. Go look at some pictures. And let's just confirm that we're not crazy and that these are things that we have an appreciation for and that they match all the behaviors that we expect. Okay. So let's look at some examples. All right, remember that the total wave function of the hydrogen atom, which I'll write psi total, takes in, as far as we know, 3 numbers. We need the n number that specifies 1, 2, 3, the L number that specifies whether we're SPDF, and then the m number, which specifies which one of the p orbitals or d orbitals we're in. So it takes 3 numbers. And we know that it's a product of the radial part of the function. So it's this radial function that we just derived, plus times the spherical harmonics, right? So it's a product of 2 functions. And these are well-tabulated functions. We can look them up on the internet. Both are tabulated online. And I'll post I don't think you need these for the homework this semester, for today, for this week. You don't need these for the homework, but I'll post them later. All right, so we have a product of two functions. And so I'm going to make a table here. Let's just tabulate some of these functions. So each function, each orbital is labeled with 3 numbers, N, L, and M. Right, we'll start from the ground state, which of course is 1. If N is 1, the largest value of L is 0. If L is 0, the only value of M is 0 as well. So this is our first orbital, right? We call this the 1s. Call this label. This is the 1s orbital. Right? And this function, once you look them up, is this wave function. Is 1 over the square root of pi times a naught to the 3/2. We'll talk about this a naught number in a second. Times e to the minus r over 8 naught. Okay. And this should be a function of r, theta, and phi. It should be all of those, right? And the 1s orbital is just a function of r. Remember that the L equals 0 orbital looks like a sphere. It has no angular dependence. And we have a sense that the 1s orbital should look like a sphere. It should have no angular dependence at all. The electron can be anywhere. So the wave function's only dependent on r, right? So that means that the value of the wave function, or the probability that you find the electron somewhere in the atom, only depends on the distance. So let's look at that function. We kind of know what this looks like in XYZ space. Right, I could draw, right, this 1s orbital, right, as a sphere, right, something like that. Right, it's got this 1s orbital, but this sphere is just a fixed radius, right? So this kind of is what the 1s orbital looks like at a fixed distance, right? But the wave function is defined for all values r. So the electron doesn't really exist in a sphere. It actually exists kind of, it can be in any distance. It's not at one particular distance, but it can be in any distance. Right? But you can imagine that if I freeze the electron at one specific r, the wave function has that value at all angles, right? So what I've taken here is a snapshot of the electron at some very specific distance r, right? And this is r fixed. Right? And it only depends on the angles, right? But if I were to instead look at the wave function on the r-axis instead, sorry, psi, right? That looks like e to the minus r over a naught, so it has some value at r equals 0 and it decays out. So in terms of angles, it looks like a sphere, but in terms of r, the wave function is an exponentially decaying function that gets, in some sense, weaker as it goes out. Right, so it's kind of a weird thing to think about, right? But the 1s orbital is not a sphere. It has the shape and the symmetry of a sphere. But you can kind of think of it as if you think about the probability as, like, imagine the electron being like a tent, like you're tinting a window, and the more probability you can have, the more tinted the wave function, different the color is. So as the electron becomes more probable, the shell that it exists in becomes darker and more opaque. And so what you can imagine is that what this wave function looks like. Yeah, it looks like a sphere, but it exists at all distances r. It's just a continuous spherical distribution that becomes less and less and less opaque as you go away. Right? So there's some region of the sphere that's very dark and you can't see through it, and then it gets increasingly more and more thin as you stretch out. It's kind of hard to imagine that in your head. Okay, but the idea is that it does look like a sphere. It's just that it's an infinitely thick sphere that gets thinner and thinner as you go out. So that's why we often draw these pictures that look like a circle or a lobe or whatever. But the idea is that we fixed the distance that the electron can be at in those pictures to some amount. And we're just plotting the shape of the wave function at that fixed distance. Okay, let's look at the next one. Let's move up to 2, 0, 0. Right, this would be the 2s orbital. It has a slightly more complex structure. 1 over 4 times the square root of 2 pi times AO to the 3/2 times 2 minus R over A naught times E to the minus R over 2 A naught. So let's look at this function compared to our 1s orbital. If you look at it, the 2s and the 1s is pretty similar. There's some number proportional whatever A naught to 3/2 E to the minus R over A naught. But looking at n equals 2, we have this new linear function that appears in the parentheses, this 2 minus R over A naught. Right, so we have this linear function. Right, this kind of looks like 1 minus x e to the minus x. See that? This function is going to have a different behavior. Right? There's going to be values for x or r here that are negative, where the wave function changes signs, right? Where r over a naught is a larger number than 2, this function should be negative. Not only that, there is a point where r over a naught is equal to 2, where this function is 0. Right, so this function changes signs and goes to 0. So let's look at that function. Let's look at the radial function in terms of r. Right, if r is 0, this function is positive. 2 to e to the minus r. So it starts at some positive value. And then it decays as r gets bigger. And then when you get to r over a naught is equal to 2, it goes the other way. Like this. Right? It changes signs. It goes to 0 where r over a naught is equal to 2. It goes negative, and then eventually it decays as the exponential term gets larger. Smaller. The kickoff. Right, so that you have a change of sign here where r is equal to 2a naught. Right? And this is a positive sign here and a negative sign everywhere else. Right, so what does this look like in terms of angle? Well, we have, this is still spherically symmetric. There's no sign, there's no angles here, right? There's no phi or phi. So it still looks like a sphere. But let's think about the thickness or the opacity of that sphere. We have a positive opacity here, and then it gets thinner and thinner and thinner, and then it goes to 0, and then it gets thicker and thicker and thicker in the opposite direction, becomes a negative phase instead. So what we have kind of, it looks like a jelly donut, a spherical, like a what do you call the Dunkin' Donuts? The little, they're not called munchkins, are they? Yeah. Dunkin' Donuts. I can't remember if that's Timmy's or not. Tim Hortons has it too. I forget what they're called.
Timbits.
There we go, Timbits. Yeah, we got a donut expert here. So think about like a munchkin that's filled with jelly, right? So we have a jelly core, and then there's an interface between the donut cake, which is negative, and the jelly. Right? And so there's a region, there's a shell, an infinitely thin shell where there is no probability at that transition between the positive and the negative point. So it still looks like a sphere, but instead it kind of has a core inside of it of different shapes. So it kind of looks like two concentric spheres, like this, right, where the internal part is negative and the external part is infinite, or sorry, is negative. Sorry, this is negative and this is positive. It's a positive quarter. Okay. Remember, the positive and negatives are just a phase. They're just a negative sign and a positive. Okay, so it just tells you something about the stage of the function, which will play a role later on. Okay, but it's the same idea, but it has a different shape. So you can imagine if I go to the 3s, what that might look like. Right? We just give us that, go back to think about the harmonic oscillator, or any of the wave functions we've looked at. We know that they kind of look harmonic, right? You have a wave function that has half a phase, right? Half a period, which means it's either all positive or all negative. We have one going a whole phase, meaning it changes plus to negative. Right? So we go from plus to negative, and so you would expect, okay, the next one's going to be plus, negative, positive, right? You get 3 half periods, and then in equals 4, you're going to have 2 whole periods, or 4 half periods, plus, negative, plus, negative. Right? So what you're getting, you're going to get continual oscillations of this function. And so the idea is that for 3s, right, we can just kind of assume that the function is going to look something like this. Like this, right, where we have a negative, a positive, and a negative region. And that function is going to look like it has 3 concentric circles of density. Like this. And so on and so forth. So again, these are just, right, this is just looks kind of like oscillations. They're not sine waves, right? Because sine waves are oscillating forever. And these wave functions, by definition, can't oscillate forever, because we showed that at small r, they look like a polynomial. At long r, they look like exponential. So they don't look oscillating at the ends. So you can't use sine and cosine here, because sine and cosine oscillate always. But we know that in the middle somewhere, just like the harmonic oscillators, they have to look like they oscillate. They have to look like waves. And now you're starting to see that wave-like behavior that we would expect. Functional R, right? So the idea is in some sense, the radial function determines the oscillating frequency of the wave-like behavior of the electron in the orbital. So you can imagine as you go to 4s, 5s, 6s, 7s, 8s, 9s, 10s, which of course become increasingly irrelevant for chemistry, these wave functions just start to look like more and more complicated donuts. Okay, so those are our s orbitals. Right? S orbitals are basically just spherical waves. That's all they are. It's a very simple wave that has no preference in direction, an isotropic wave, right? And it has states of increasing frequency, right? Which are correspond to different spherical waves of different frequencies. And in fact, when you look at physics and you look at people who do collisions and scattering and all sorts of different things, they call, and in fact, what's it called? The seismologists, the guys who study earthquakes, they also have different types of course, earthquakes are wave-like behaviors. There's 2 different, what do you call it? In earthquakes, there's a wave that goes like this. It makes the earth undulate up and down. And there's a wave like this, a transverse wave that makes it undulate left and right, or a compression wave like this. And they call one of those an S wave, which is this, right? It's this one. We call this a P wave. It has the same symmetry. You can imagine that the S wave is the Earth expanding away from the center. And the P wave is the polarized one, where it's basically stretching the Earth perpendicular to its radius. And so this S and P behavior is very similar. It's just something that you see with waves on spheres in general, including in seismology. Just that we also see it in hydrogen. Okay, so let's do something a little more interesting. Right, for n equals 2, we also have L equals 1, the p orbitals. So let's go look at those right now. And there are 3 choices There's the 0 and the plus or minus 1. Right, and what we're going to see in a second, one of these is the z orbital, the pz, and the other one's the x and the y. Let's figure out which one it is. All right, so for the 2, 1, 0, the wave function is 1 over 4 square root of 2 pi AO to the 3 halves times R over A naught e to the minus R over 2 A naught times cosine of theta. Aha, now we have a theta term. So now in our p orbitals, we're starting to see angular wave function depends on the angle theta, which is the angle relative to the z-axis. Okay, so let's figure that out. So if we hide that cosine of theta, this function just kind of looks like r times e to the minus r. Okay, so this is positive for greater or r greater than 0. And then for negative values of r, the opposite side is negative. So this is less than 0 for r less than 0 and greater than 0 for r greater than 0, which there is no r less than 0, but so that doesn't matter. So it's greater than 0 for r equals 0. And then we have the cosine term, right? And cosine is maximum at 0 and pi, right? 0 and 2 pi. So this is equal to plus 1 at theta equals 0 and minus 1 at theta equals pi. Okay. So what I can do now is plot my function in x, y, z. Okay. And if I look at this e to the minus r, this just looks like a decaying function times r. Okay, so at x equals 0, it's going to be 0. Or at r equals 0, it's going to be 0. And then let's look at cosine. If cosine theta is 0, which means we're on the z-axis, the function is maximum. Okay, so I know that the function is going to go to some positive and negative value on the z-axis. Okay, and where is this function 0? Well, it's 0 at r equals 0, but it's also 0 on the xy plane because that's where theta is equal to pi over 2. So I know the whole xy plane, this function is 0. So I can kind of like draw some lines here on the xy plane and just draw a little square through here. And I know the function is going to be non-zero in this region. Or sorry, it's going to be 0 in this box. And it's going to be 0 in this box. So that means that the wave function only exists above and below the plane of the atom, or of the xy plane. And the function's maximum at theta equals 0 and minimum or maximum of another local at pi. All right, so let me think about this function as I sweep away from 0 and I move down the z-axis. Right, so I'm taking a vector pointing z positive and I'm just rotating it along the z-axis towards negatives. The function starts maximum. And then as I get to pi over 2, it's going to go to 0. And then as I move away from pi over 2, it's going to get negative again until I reach a maximum there. I get the same behavior on the other side, like that. Right. On this function is other in regions outside the xy plane, it's still spherically symmetric. No matter which, as long as I'm at some fixed theta, as long as theta is fixed, I have the same value for every phi. So every value of x, y in a circle around a certain angle is going to be the same value. So these lobes also are spherically symmetric or cylindrically symmetric. So we get these kind of like these peanut-shaped lobes like this. And one of them is going to be a positive value. And one's going to be a negative value. just color this one negative. Right? This is my negative one, and this is my positive. Right? And so we call this the 2pz orbital because it's the electron lies along the z-axis. Remember that theta is the z angle and phi is the xy plane. There's no phi direction. There's no phi dependence here. So no matter what phi is, the value looks the same. So each of these lobes have to have that symmetry. So it's got that peanut shape that we know. And that comes from that cosine behavior in the function. Now, we should automatically know what px and py look like. We just take that orbital and flip it onto the other axes. Right, so the px orbital is going to look just like the pz orbital, except it's lying on the x axis. And the py orbital is going to be lying along the py orbital. We already know what they kind of look like. All right, so let's just double check the math works for that. Just want to cut this off. Crash on me? It did crash on me. I felt it in my bones. And I lost all my notes too. Maybe I didn't. Maybe I'm lucky. I didn't lose them. Oh, thank God. Okay. I just want to erase this so we can add a little more space. All right, so let's look at the other two orbitals, right? I know kind of implicitly that these are going to look like px and py. Well, we're going to see a complication in just a sec. Let's write down the formula for this. If I don't have on this page, just a sec. Okay, sorry about that. So we get 1 over square root of 64 pi AO to the 3/2 R over A0 e to the minus R over 2A0. Okay, that looks exactly the same as the function up, but the coefficient's slightly different. 4 pi instead. Right.
Sure, it's A0.
It's A0, yes, yes, and I'm going to define that number in a second once we're finished here. And so it's exactly the same formula there, but remember we're rotating things on the xy plane, so we're going to have a different angular dependence. The spherical part, the radial part, is still the same. It's a p orbital. But so instead of cosine 0, we're going to get sine of 0. Right? What is that going to give us? Well, that's going to give us functions that are 0 along the z-axis, right? Because cosine is maximum at pi over 2. Pi over 2 from the z-axis is the xy plane, right? So these are going to be maximum in the xy plane. But here's the problem. We have to now polarize the function either along the x or the y. Theta doesn't give us that. That just sine of theta puts us in the xy plane. Now we have to point them in either the x direction or the y direction. That's going to be a phi number. And when you look at the solutions for it, they're complex. UDI phi. The only difference between m equals 1 state and n minus 1 state is that you have a negative I phi and the other one a positive I.
Can you play up to square?
Sure. So I'm being a little late. Yeah, you can pull out the. Yeah, so it's exactly a half of the number up there. Because 4 square root 2 pi would be 32 square root 32 pi. So it's factor 2 not there. So we now have a complex orbital. Why is it complex? Unfortunately, we've by solving the problem the way that we did, we've condemned ourselves to having complex functions on the xy plane. Now, why is that? remember how we defined angular momentum in our system. We knew the length of the angular momentum, L squared, and then we knew one of the directions, LZ. We chose the Z direction. So we have good sense of the general direction of the electron's trajectory on the Z-axis. So in our Z-polarized orbital, 2pZ, everything is real. And it should be real because we've defined our system to be real on the Z-axis. We can measure the Z-axis behavior. So all of the results, all of the measurements of our Z orbitals, Z-polarized orbitals, are real. We don't know anything about X and Y, right? That was the entire point. When we choose Z, we only know one of the three. The X and the Y are completely undefined. And so anything that's defined on the XY plane, we don't know anything about its behavior. So by definition, it has to be delocalized on the XY plane. It has to be anywhere on the XY plane because we have no knowledge of where it is. And so we get an e to the I5. Right? Remember, when we don't know anything, we get a complex value. Right? E to the I5 means it can be anywhere on the XY plane. Right? And so what's the difference between the plus and the minus state? Well, one of them is going clockwise. One of them looks like a clockwise rotation, angular momentum, and the other one's counterclockwise. All the differences. One is a clockwise rotating electron. Sorry, this is counterclockwise rotating 2p electron. And this is minus I phi, is clockwise rotating. Okay, so that doesn't really help us at all. Right? Well, how the hell did we get 2px and py? We know that when we draw pictures of them, we do the math and do the chemistry for electrons in those orbitals, like when we look at pi orbitals in chemistry, we know that they have x and y, or they look like pz but rotated. So how do I get from this representation into something that we see in real space? Well, the important distinction is, yes, the wave functions are complex, but our observations never are, right? Anything that we observe that has a complex wave function, we see the real projection of it on the real space, right? Anything, we can have complex waves, nothing wrong with that. But anything we measure about it has to be real. That's the whole point of quantum mechanics. So there must be some way to massage this and interpret this structure and massage it in such a way that gives us real orbital value. Because that's what we observe in experiment, real orbitals. We observe a px and a py. So how do I combine these to get px and py? So this is it kind of seems like an odd question to ask, but this is a really important concept in chemistry. And so going from plus or minus e to the I phi to 2px and 2py, this process is called hybridization. We hybridize the orbitals. Okay. Heard this term before in organic chemistry. Talk about sp3 hybrid orbitals in orgo. We talk about the methane, the methyl, the carbon atom in organic chemistry is sp3 hybridized. That means that its valence s orbital and its valence p orbitals are all added together at equal weightings to give you 4 equal identical orbitals called hybrid orbitals that are constructed from the s's and the p's. So what we're going to do is we're going to construct hybrid orbitals from our p orbitals to give us hybrid orbitals that are real from a collection of complex orbitals that we can't really directly measure, right? I'm always allowed to do this. I know it sounds like I'm hacking it, like in the sense that I have some solution, and what I'm going to do is I'm going to add and subtract them together to get new solutions. And you're going to be like, well, that is a stupid, like that seems like it's cheating, but it's not. We have been doing this process for a long time. In problem set 1, I set you guys up a problem where you look at the deflection state of an electron. It's either up or down. And then I ask you at the end of the problem set, what's the generic state for the electron before it ever goes through any of the measurements? What's the most generic state that you can describe the electron? And what you guys showed was the most generic state was not only just up plus down, but it was the combination up plus down plus or minus the combination up minus down. Right? You combined all the orbitals together as generically as possible, and that generic addition of these base states is the actual initial state of the atom, right? The actual state of the system is the sum of all the possible results. So there's nothing wrong with me taking a 2px and a 2py orbital and combining them together or subtracting them from each other. That gives me a result that is perfectly allowable and if I do it the right way, I can get rid of the i's if I make the right choice. So I can always add and subtract solutions together. So what I'm going to look at now is I'm going to create two new wave functions for our 2p orbitals, psi and psi prime, which are going to be equal to phi 1 plus 1 plus phi 1, sorry, this is the plus 1 state and the minus 1 state. All right, so I'm going to add them together and I'm going to divide by the square root of 2 to normalize them. And then I'm going to define another one as the difference of the two. And so the 2 states times 1 over the square root of 2. So let's think about how that works. All right, I'm going to add them together and subtract them. Take the sums and differences. Well, when I add them together or subtract them together, I'm going to get a bunch of things that factor out. I'm going to get to a bunch of signs and a bunch of coefficients. Everything gets factored out. The only thing that's different between the two is this value of EBI5, right? Because for one, it's positive, one, it's negative. So all the other terms can't get factored out. So this is going to look like 1 over, what did you factor out? 8 square root of pi, AO to the 3 halves, R over A naught, E to the minus R over 2A naught, sine theta. And then what I have now is E to the I phi plus E to the minus I phi times 1 over the square root of 2. Okay, so I'm just adding them. And again, on the other one, I get the exact same thing. But the only difference is E to the I phi minus E to the minus I phi over 1 over the square root of 2. Okay, so all we have to do is figure out what these sums and differences are. Recall E to the I phi is cosine of phi plus I sine of phi. Right? So that means that E to the I phi plus E to the minus I phi is equal to cosine phi plus I sine phi plus cosine theta phi minus I sine phi. Okay. You can see the signs cancel out. So this is equal to, come on. Oh, the room is getting hot and my computer does not like it when it's hot in here. And I've lost a lot of space. Okay, hold on a second. So let me copy a few things over from my previous notes. Okay, so there we are. All right, where were we? Okay, so we had this. Okay. And what we're going to show, what we showed, is that when you sum e to the I phi and e to the minus I phi and divide by a half, well, let me get rid of the half because we didn't do that. You get 2 cosine phi, right? We get the I signs cancel out, and you're just left with the cosine. Now we can do the same thing for the difference. Right? This is going to be cosine phi plus I sine phi minus cosine phi minus I sine phi. Right? Now you can see that the cosines cancel out the sines. So this is equal to 2i sine phi. Okay. So if I take 1/2 e to the I phi plus e to the minus I phi, I get a real function, cosine. Okay. And if I take 1 over 2i e to the I phi minus e to the minus I phi, I get sine of phi. Okay. So this is why we can add and subtract them, right? The key is that we take our base states, which are these complex states, and if we add them together, we take an electron that is going clockwise 50% of the time and add it to the state where it's going counterclockwise 50% of the time. What we get is an electron that has behavior that looks like cosine phi. And if we take the opposite combination of them, we subtract them from each other, then we get sine phi. Okay? So this is why we make the combinations, is that now we get the I goes away completely, and we're left with combinations that are real. So what this means is that the 2px orbital, I'm hoping, one of them, we'll double check, is going to be 1/2, 1 over square root 2 over 2. Sorry. Psi 1, 1 plus 1 plus psi 1, 1 minus 1. And what that should give me is so let me put it over here. So I have 2, so 2, 1 plus 1 plus 2, 1 minus 1 is equal to, let me copy it all over, this whole thing. Right, but the e to the I phi has gone away. We have to multiply this by 1/2. And we get cosine of phi. Okay, and if we take the negative version of it, we get sine of phi times 1 over 2i. Okay, so one of them is a cosine and one's a sine. All right, so let's go look at what those look like on a graph. All right. So my first function, so we're going to say that psi of 2px kind of looks like r e to the minus r over 2a naught times sine of phi times cosine, sorry, sine of theta times cosine of phi. Let's go ahead and look at what that looks like. So sine of phi. Right, remember, so if r is 0, this function is 0. And it's defined for all other r's. So this function has a point here. Right. Sine phi, sine of theta is 0. The function 0 if theta is 0 or pi. So the z-axis is a nodal line. Can't exist anywhere on the z-axis. This is all zeros. Right. Sine of theta is maximum at pi over 2. That's the xy plane. All right, so this function is going to be somewhere in the xy plane. And then cosine of phi is maximum at 0 and pi. So it's at x positive and x minus. So this function is going to be max at theta equals 0 and theta equals pi. So that's going to be here and here. The function is also 0 along the y-axis, right? Because cosine of phi is cosine of pi over 2, and that's 0. Right. So now we have a nodal plane that lies along the YZ axis. Yeah. And this function exists only on the x-axis. And of course, one of them is a different sign than the other because negative cosine. So I got a negative pole here and a positive pole here. All right, so there's our 2px orbital. Inside 2py looks the same. It looks like re to the minus r over 2a naught sine of theta. But we have a sine of phi instead, right? Remember, we get from the difference, we get a sine of phi, right? And of course, that now leaves us on the y-axis instead of the x-axis. The x-axis is phi equals 0 and pi. That's 0. And so this function lies only along the y-axis. Here and here. It's a negative for negative y. So 2py. Okay. So the px and the py orbitals come from the fact that we don't really have any information about the x and y axis, right? So that means that the electron moves in a complex way in the xy plane. And so when we if we have complex behavior, we can only observe the real part of that behavior. And the only way to get real part of a complex motion is to take a sum of the counterclockwise and the clockwise motions and add or subtract them together to get the real part of that motion. And one of the trajectories gives you a cosine and the other one gives you a sine. And that means that in the real axis, these look like motion along the x-axis and the y. It's just a consequence of the complex math. Right? It's not really what they're doing because that in some sense contradicts our knowledge of the x and y plane. We don't know anything about it. But the nature of not knowing the x and y plane, knowing that it's a complex wave in that plane, means that we have two imaginary results. We have two real results, and those real results turn out to be a cosine and a sine projection, one of those being on the x, one being on the y. Okay. So it's just a coincidence of the math, the fact of the wave nature of the system. It's just a consequence of the results. Okay. They're really powerful, assumption that we make. We have complex behavior, but it's fine. It's okay for it to be complex. We just always see the real part. And that's going to look like this. Okay. We're running like half a lecture behind the other class, which is okay. We're actually catching up. We were 2 lectures behind, now we're half a lecture. Okay. I want to talk about one more thing. I'm not going to do too much more math anymore. We'll continue with orbitals next class. Finish up our discussion. I want to talk about a side note, which we haven't discussed yet. Is this number A0? Right. So since I've introduced this these wave functions in class to you, I've mentioned that this A0 is this new constant, and it's got some length scale because the exponential e to the minus r over ma0, that exponential needs to be unitless. And you can't have units in exponential. So N doesn't have units, just a number. So A naught has the same units as R. Right? So it's a length scale. Let's see if we can appreciate what that length scale is, and maybe it'll teach us something to think about when we look at hydrogen's orbitals a little more carefully. So I want this to motivate the rest of our discussion, but what's called A naught number. Right. This A naught is what's called the Bohr radius. A naught. Okay. And it's equal to a very specific set of numbers. My is going to crash. 3, 2, 1, crash. I have to clean my computer out. Okay. I'm going to write down the numbers. So they're determined based on a bunch of numbers we've already seen. A naught is a constant derived from other constants. And I'm going to split them into 2 different colors. All right, so A naught is defined to be 4 pi epsilon naught over E squared. I've seen that in the electrostatic units. When they do electrostatic. Times H bar squared over ME. Think about where those numbers come from. Well, remember that the electrostatic force, the potential electrostatic force, a function of R, is equal to minus E squared over 4 pi epsilon naught times R. All right, so we can see that this, whatever this number for E squared over 4 pi epsilon naught is, right, it's in there. Right, so it's got half of this number has to do with the electrostatic strength. Okay. What about the H squared over ME? Well, the centrifugal force was equal to H bar squared over 2 ME R squared L plus 1. Here's our other one. Right? So we have 2 terms. Something that looks like, right? This kind of looks, if we look at it roughly, this kind of looks like a ratio of the electrostatic force at fixed R over 2 times the centrifugal force. A fixed distance. All right, getting rid of all the R's. So what we could say is that this is roughly equal to the kinetic energy of orbit divided by the strength, let me do a different color, of EM attraction. All right, so whatever this bond, like whatever this R naught is, this A naught is, it's a balance. It's some number that teaches us a balance of the 2 forces in our system. Remember, the electron brings in 2 things. It brings in this centrifugal kinetic energy, and it gets some potential energy from its interaction with the proton. And we have always talked about these things being at balance, right? The stable orbits are the ones where these 2 forces are equal to each other and opposite, right? And so A naught is some ratio of these 2 forces, right? It tells you something about the relative fundamental balance between the 2 implicit forces in the hydrogen atom, right? So you can kind of think of this as the fundamental ratio
of energies in hydrogen atom. Right? And that turns out to give you a length. It's a length scale, and it's exactly 5.291772 times 10 to the minus 11 meters, which is equal to roughly, I got too many equal signs here, sorry. 0.53 angstroms. All right, so what does this tell us? It says that there is some fundamental sticking force between an electron and a proton. And there's some fundamental kinetic energy due to the orbit of that electron, which is proportional to h squared over me. The bat ratio of those two determine a length, which is in some sense the fundamental length of the orbit of the orbits in hydrogen, right? And it's half an angstrom. We're not exactly sure how the different orbits correspond to A naught, but they must be proportional to A naught because A naught shows up everywhere in the wave function. It has to be something to do with A naught, right? But this is a nice way to think about this is like this, right? Imagine I have two atoms, two hydrogen atoms at some distance from each other, and their electrons are at exactly A naught. Imagine I bring them in together like this, and then I bring my two atoms together to form a molecule. I bring them together to form a molecule, right? So I form H plus H goes to H2, right? What would that kind of roughly look like? Well, it's kind of like I've added some connective glue between those two 1s orbitals. Right? And this is A naught. We'll say that this is roughly A naught, and this is roughly A naught. Right? So the distance that the bond forms, right? The bond length looks like 2A naught, which is 1.06 angstroms. Right? And the hydrogen bond length is about 10% smaller, about 0.9 angstroms. Right? So A naught, right, is the fundamental length scale of the electron in an atom. We'll have to prove that next class, that A naught has anything to do with hydrogen. But it's some length scale, so we could say, okay, well then the lowest energy state is the one where the electron is closest to the hydrogen, the proton. So it's going to be like A naught, it might be 2A naught, who knows, some fraction of A naught. But it's probably close to A naught. And so that means if you bring in two electrons in the 1s orbital, their average distance between the two protons is going to be 2A naught. And so the bond length is roughly 2A naught. It's equal to roughly an angstrom. And that's where bond lengths typically are, right? Most bond lengths are anywhere between 0.8 angstroms to about 1.5 angstroms for pretty much any bond you can imagine. Okay, and the reason why bond lengths are that length is because A naught is about half that length. Imagine if you cranked up the strength of the electromagnetic interaction, the bonds in chemistry would get shorter. If you turned it down, or you increase the kinetic energy of orbital angular momentum, right, the electrons would be further away on average and bonds would get longer. So chemistry is entirely determined by this, right? This is just what I would call the chemical length scale. Right? This determines all bond lengths in chemistry. And the reason why we use angstroms for everything is because it's just the natural unit, right? A bond length is roughly unity in an angstrom scale because half a bond length is set to be about 1A naught, which is half an angstrom. Right? This is why we use angstroms. It's just a perfect scale. It's exactly unity, roughly exactly unity at the kind of canonical bond length we would expect at 2A naught. So we haven't really determined anything interesting or properties of of hydrogen, but what's fallen out of the math that we've done is this A naught number, which is a combination of all the potential terms, all the forces that the molecule, the atom feels. And we haven't done any other property math. I haven't told you anything about the properties of these orbitals. We haven't even looked at the energies yet. But there is this property embedded in their structure, which is this A naught. It determines this length, this natural length scale for chemistry, which is A naught. And it's a function of all the fundamental parameters, all the fundamental constants we talked about. The only one that's missing is the speed of light. About the only one. And it gives us a length that gives us chemistry, where chemistry comes. Now, doesn't give us chemistry in the sense this is what causes things to react. That's a different conversation. But it, at the very least, tells us something about chemical structure. Right? Chemical structure is going to be on the order of 2 times this length. Okay, so that comes out for free from the hydrogen. All right, so we didn't have to do anything to figure it out. What we do need to figure out is to prove that the electron, in fact, on average, is around A naught in the hydrogen. I haven't really quite figured out. It could be 2 A naught, it could be 3 A naught, I don't know. It could be 1 A naught. So I'm not exactly sure where the electron is. I'm just making a kind of a guess. It's an educated guess. Seems reasonable. So we just need to confirm it. And that's what we'll do next class. Okay, let me see if I have any other quick comments I want to make to you. No, let's just stop there. Okay, so we'll stop there. And then what we'll do next time is we'll go calculate this exact distance for the hydrogen atom and show that it's very close to A naught. And then we'll go from there. Okay, you guys have a good one.
Oh, yeah.
Are you on side, Brandon?
Thank you, you too.